we are getting closer to meshing the idea. No, we're here. We've made it. We've made it to how does this deal with definite integrals? Or how does this deal with integration in general? Okay. Why have we been doing all this weird area and sum stuff? How does it relate to calculus? Okay. So here's what we're going to do. Do you remember when I showed you that graphic on GeoGebra of our rectangles getting smaller and smaller and smaller? Okay, and the smaller, I guess I should say the thinner we can make our rectangles, the more accurate we are going to be. Do you agree? Okay. What we're going to do today is we are going to take our rectangles and we're going to make them infinitely small. Okay, we're going to make our rectangles infinitely small so we can add them together to get exact area. Yeah. Oh, no. You here?
Yeah.
Okay. All right. So we need to find a way to sum up an infinite number of rectangles, is essentially what we're going to do. Okay? We're going to sum up infinitely small. Let me rephrase this. We are going to sum up an infinite amount of infinitely small rectangles. Wrap your head around that for a second. Okay? This is how we're going to do it. Okay, so don't write anything down right this second. But let's talk about when we did like the right and left hand sums, right? We figured out how wide they were, delta x. And then we multiplied it by all the different heights. F of x1, f of x2, f of x3, f of x4, right? Okay, so this right here, delta x times f of x sub k, that's representing the width of the rectangle times the height. What we're going to do is we're going to add them up from k equals 1 to n, but we're taking the limit as n goes to infinity, which means we have infinitely small rectangles and we're adding them up, and there's infinitely many. Write this down. Right, exact area is that. Yeah.
So that's going to be like the most, is it exactly or is it?
It is exactly. What?
I said brain machine broke.
What? Okay, but see, in Unit 1, we had this concept of limits, right? We had this concept of limits in Unit 1, where do we really have an infinite number of rectangles? Like, we're approaching infinity. So we're approaching these rectangles getting infinitely small, and we're approaching having infinitely many, okay? So as we get smaller and smaller and smaller with our rectangles, we can use this summation using a limit to actually calculate the exact area. Okay? If it helps, imagine just drawing lines right next to each other, right? Until we color in the whole thing. That's what we're adding together. Okay. What you just wrote down, we are going to call that, it's actually, we can write it like this. It's a definite integral. From A to B, the integral from A to B of f of x dx is actually finding us the area under the curve, which we're going to do by using this crazy thing I'll show you how to calculate. Okay, so what's the difference between this integral and ones that we've seen before?
It has the two numbers.
And there's the two numbers, there's a range from A to B. Okay, so a definite integral will have numbers attached to that integration symbol. An indefinite integral is when we don't have those numbers and we have to write the plus. All right? So, a definite integral is defined as the exact area under the curve, which we are going to find by using a Riemann sum. Now, there are a couple properties, I think that's what's next. Yep. There's some properties that we need to go through of a definite integral. Some of them will be important for today. Some of them will be important for Monday. So we're just going to write them down right now. The integral from A to A of any function is 0. I'm basically asking you, what's the area from A to A? Have you gone anywhere? The integral from A to B is the opposite of from the integral B to A. Kind of like working backwards. The integral from A to C added to the integral from C to B, notice how those C's match up, is the same as the integral from A to B. We keep talking about the integral from A to B, which is why they throw C in the middle, but I want you to imagine that like C is in the middle of A and B, right? If you want to hear it with numbers, the integral from 1 to 2 plus the integral from 2 to 3 equals the integral from 1 to 3. Okay, here's what's important for today, and we've talked about this with indefinite integrals. But if we are adding functions inside of our integral or subtracting, we can separate that into the sum or of two separate integrals. But it's important for you to know that it still works with definite integrals. And the same thing with the constant rule. If you have a constant multiplied inside of your integral, it is okay to move it to the outside, even if it is a definite integral. We will work with those bottom two properties today. The top three we will work with more on Monday, but you'll have them written down, so that'll help. Now, before we get into actually calculating this thing that you have been intimidated by, since I showed it, we need to do a little bit of prep work, okay? We're going to go through some limits. okay? So that when we're doing Riemann sums, we can have some shortcuts, okay? So it is possible that you are going to get the limit of this guy right here. Basically, we need to review some summation rules with our limits so that you guys remember how to take the limits. Okay. All right, so we have the limit as n approaches infinity of 1 over n times, what's the sum from k equals 1 to n of 1? Yeah, we're summing up 1 n times. Our limit is 1. Okay. Okay. You will see this summation pop up in your Riemann sums. Okay, what's our shortcut for the sum from 1 to n of k? Okay, essentially we have the limit as n approaches infinity of n squared plus n over 2n squared. Flashback Friday, our limit rules. Okay, so we can divide everything by n squared. That's one strategy. What's another strategy?
N squared divided by 2n squared equals 1/2.
Okay, since the degrees are the same, we can look at the coefficients. Third strategy. It has a cool name. L'Hopital's rule. We have infinity over infinity, so you can take the derivative, right, until we get 1. Okay, basically what I want you to realize is that when you have this right here, and we write it in closed form, our limit's going to be 1/2. This will pop up often in your Riemann sums. I'm hoping you're seeing a pattern here. Okay, so we have 1 over n cubed, the closed form of the sum of 1 to n of k squared.
N times n plus 1 times 2n plus 1 equals 36.
Okay, I don't have that multiplied out. And I don't think it's worth our time to multiply it out. In our numerator, we're going to have 2n cubed, blah, 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 blah. In our denominator, we are going to have 6n cubed, blah, 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 blah. What's our limit? 1/3, because we're looking at that 2 over 6, those coefficients. Interesting. Any guesses of what this limit's gonna be?
1/4.
Let's see, write it down. So we have the limit as n approaches infinity of 1 over n to the 4th. Closed form of what the sum of 1 to n k cubed.
Times the quantity n plus 1 over 2 all squared.
So in our numerator, we're going to have n to the 4th, blah, 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 blah. In our denominator, we're going to have 4 n to the 4th. Trevor, what's our limit? Yes, it is. Okay? You will see those 4 limits pop up in your Riemann sums. We're going to be working with polynomials. Okay? All right, so let's talk this through again. Don't write anything down right now. We are going to take a function from A to B. Okay? And we're going to partition it. What does partition mean? Split it up into parts. Okay? We're going to partition it into parts from A to B. X of 1, X of 2, X all the way to X of n. All right? Now, we're going to denote it with i's. So any one of those is arbitrarily x of I. Okay? And our intervals are going to go from x of I to x of I plus 1 or x of I minus 1. Okay? So the width of our rectangles would be from one x to another. That's what it's saying. Okay? C is anywhere on that interval. We have this Riemann sum, which I've shown you. It looks a little bit different. But essentially what it is saying is that on this interval, this is the width of our rectangles. And then this is the function value at any given x. Okay? Where our x's are x of I plus 1. Okay, they're that far apart. Okay? What we are going to do is we are going to take these n rectangles and we are going to take the limit towards infinity. Okay, what does that do to our rectangles? That makes delta x infinitely small. And as we go towards infinity, we have essentially an infinite number of rectangles that we are adding up. Okay? You've already written this down, but as we take that limit towards infinity, we are finding the exact area under the curve, which is what the integral from a to b of f of x dx represents. Okay? Now, I taught you 4 different ways to find approximations of area. Okay? Now, this looks more like what we did with right, left, and midpoint. Okay? First of all, we don't want to mess with midpoint. All right? We're not going to find the midpoint of all these arbitrary values. Okay? I'm going to tell you right now, it is going to be in our best interest to use the right-hand rule with our Riemann sums. Okay? So we're going to use right-hand rectangles. So when we're plugging values in to find the height of our rectangles, if we're going from A to B, do we start at A for our right hand? No, we don't. We start at the right side. So x sub k, whatever we plug in right there, is going to be A plus, we're going to say k times delta x, because we have to write it in general. So our first rectangle would be, you know, a plus delta x. And then our next rectangle would be a plus 2 delta x. And our next rectangle would be a plus 3 delta x. You see where I'm going with this here? Okay, so that's how we're going to write it in general. Are you ready? Please be very organized with how you take these notes. There is a lot to these problems, okay? And the order in which we do things will be important. So, we are finding the area of y equals x squared from, what does it look like? 0 to 5. So you don't have to draw the picture, but I have it for you. In your notes, you could at least write y equals x squared from 0 to 5, like area under y equals x squared from 0 to 5. Okay. Let's talk about what this means. This means the integral from 0 to 5 of x squared dx. Okay, when we did our right-hand approximations, what was the first thing we had to figure out?
Delta x.
We had to figure out delta x. And how did we figure out delta x?
B minus A.
Okay, b minus a over n. In this case, b is 5, a is 0, n is n. So our delta x is 5 over n. Okay. That's our first job. Okay. Our second job will be to figure out what that x of k is. We're using the right-hand rule. I told you that x of k needed to be your a value plus delta x times k. So our delta x is 5 over n times k. The integral from 0 to 5 of x squared dx is the same as the limit as n approaches infinity of the sum from k equals 1 to n of, well, let's write it in general terms, right? It was f of, and don't write this down with me, I'm writing this down to remind you, f of x of k times delta x. Okay, well, what is delta x? 5 over n. F of x of k. We have to plug x of k into our function x squared. So our function is x squared, and we're plugging in x of k. Questions on that so far? Okay, so now we have to evaluate the sum so we can take the limit. This algebra isn't too bad here. We have 5 over n, k, the quantity squared, times 5 over n. Do you agree that we would have 125 over n cubed times k squared? Okay. Perfect. Our index is k, correct? So n has nothing to do with the sum. You agree? Okay. So we can move 125 over n cubed outside of the summation, and now we're worried about from k to n of k squared. Okay. The sum of k squared from 1 to n.
N times n plus 1 times 2n plus 1 over 6.
Okay. Times, I'm going to split this up. This was 1 over n cubed, and then times 125. I'm going to split those up, and you'll see why. Okay. We already know what that limit is, don't we? You can either redo it right now or remember it from before. What is it? It's 1/3. So we have it's 125 times 1/3. Our exact area is 125 thirds. Woo! There we go. Everything from our quiz we just meshed together into one problem. Can you say the answer?
Yes.
Okay. To be honest, that problem was fairly simple in regards to the Riemann sum problems that we could come across, right? We started at 0. That was pretty nice because then that made x sub k just one term, all right? And we only had x squared. There was no coefficient. There was nothing added, subtracted, anything like that. So let's look at a problem that may have a little bit more algebra inside the problem. Intent to be clear. So you don't have to draw the picture, but I'm trying to make you see that we're finding area under the curve. Our function is y equals 4 minus x squared. Negative 2 to 2 would be our interval. Okay. So what we're finding is the integral from negative 2 to 2 of 4 minus x squared dx. Ready? Let's do it. Delta x. B minus A over N. Delta X is 4 over N. What do we find next?
X sub k.
X sub K. All right, X sub K. We have to take A and add delta x times k. So you can see already how this one's going to be different. Okay, x sub k is 2 terms instead of 1. All right, that's going to make our algebra a little bit different. All right. Okay, so we have the limit as n approaches infinity of the sum from k equals 1 to n. What do we put inside our summation? Chris?
4 minus -2 over n whole.
So this would be f of x of k. So we plug this into our function and we multiply that by delta x. Okay, so we have a little bit of work to do before we can even think about doing the sum. All right, and that's fine. Here we go. Please be careful with your algebra. So let's do this. 4 minus, when we square that, 4 minus let's see,
Wait, I thought A would be equal to 3. We play next to A's and A also.
no. Because we have the very left side and we add delta xk. Yeah. So this squared, everyone agrees with me with 4, right? Okay. And when we multiply this together twice, 16 over nk plus this squared would be 16 over n squared k squared. What do you say, Jackson?
Said when there's more letters than numbers.
I know, right? That is sometimes people's biggest complaint about calculus. I remember hearing that in pre-calc, like when we did induction. You guys remember proofs by induction? Probably not. But it really freaks. That's when you really start to get into like letters instead of numbers, and it's a transition, that's for sure. All right. Well, this is nice though, right? 4 minus 4, that goes away. And we're left with a positive 16 over nk minus 16 over n squared k squared times 4 over n. We're still not there yet. Okay. All right. We're almost there. And by almost there, I mean we almost can find our sum. Let's see. We have 64 over n squared k minus 64 over n cubed k squared. Which, if you're paying attention to when we did those 4 limits, those 4 special limits, you'll see kind of the pattern that we're working with here. We have something over n squared times k and something over n cubed times k squared. That is good. That's what we need to have happen. All right? What I'm going to do is I'm going to break this up. Okay? I'm going to take 64 over n squared out of the summation, and we're going to sum up k. Minus, I'm going to take 64 out over n cubed out of the summation so that we can sum up, whoops, so we can sum up k squared. Okay, so I broke it up into 2 summations. I moved anything without a k to the outside because technically they're constants. Okay, so I'm gonna do these separately, so we can just split this up into 2 different limits that we're gonna subtract. Okay, So right here, I'm gonna write this as 64 times 1 over n squared times the sum of k is n times n plus 1 over 2. Okay, so let's just figure out what that is. We know that this right here is what? 1/2. So we have 64 times 1/2. All right, minus the limit as n approaches infinity. I'm going to write 64 times 1 over n cubed times k squared, that summation, n times n plus 1 times 2n plus 1 all over 6. You know what it is. We know that this limit right here is what? 1/3. So we have 32 minus 32/3 which is, use your calculator, I won't be upset. How many? 10 and 2/3, which would be 32/3. What?
Should be double that.
Why is it 32 thirds? Would it be 64 thirds?
Yeah, it is 64/3. I got so excited about 32 times 1/2, and then, is this better? So now is it 10 and 2/3, which is 32/3? All right. Okay. There's our exact area. Okay, here's the deal. Compared to what we just did, would you agree that this may be a little bit more intense?
Yes.
Okay. So what do you think about doing your homework tonight?
No homework.
You might not do it tonight, but you gotta do it this weekend. Okay? Now, here's the deal. Please listen. You have to practice this if you want even a chance of getting it right on the quiz or test. Okay? You have to practice it. Now, maybe you're not going to do your homework tonight. If I was in high school, I probably wouldn't choose Friday night to do my homework either. Okay? Maybe you wait until Sunday night to do it, and you're like, holy moly, I forgot what all this means. What could you do? Okay, there's a few different things. You can look in the book, you can go to CalcChat. My video that you can hear me talking right now in, you can go and watch one of the examples. You don't have to watch the whole video. You can fast forward until like that first example or this example if you want. But use your resources, okay? On our schedule, this is, I think it's 4.3a. Is that what it's called?